Hello, this is Steve Bakota. I run TI's Digital Power Group. With me here today is Chris Cooper from Avnet and Jamil Hussain from Xilinx. In previous eLabs, we went through the power requirements for Xilinx new Vertex 6 and Spartan 6 FPGAs, and also the power estimator tools that Xilinx has available. So in today's eLab, we're going to give you a little bit more detail about how you actually design and configure your power supply using TI's Fusion Power GUI. Today, I'm going to provide a demonstration of our Fusion Digital Power Designer, which is the development tool that customers use when configuring our controllers. In this specific case, I'm demonstrating the 9224. So this device can regulate it up to two individual outputs, two individual DC to DC converters, and be configured for up to 4 phase of output power. So it could be 2 outputs, each 2 phase if you chose to, a single 3-phase output with a single phase output as well, or 2 single phase. It's all depending on how you want to configure the part. In this case, I'm showing 2 individual single phase outputs, as would be used for the Xilinx Vertex 6 and Spartan 6 FPGAs. This rail is regulating to 2.5 volts. As you can see, looking through here, you have overvoltage warning and fault levels that are configurable, margin levels if you chose to do margining in your system, margin low as well, and then undervoltage warning and fault levels. Right here is showing power good, so you can configure power good with hysteresis, so it'll output a power good signal or determine when that rail is in power good. Here's on-off configuration for configuring the device and how you'd like it to respond upon configuration when it's in a system. Turn-on timing, including delay, rise time, maximum turn-on time, and fault response in that scenario, as well as turn-off timing. Down below here, you see voltage tracking. So you can not track it all, obviously. You can track based on internal rails, or you can track based on internal pins if you chose to. And it even has a tracking scale factor for things like DDR memory. If you wanted to track one rail at, say, 50% of another rail, you can do that. Turn-on dependencies are included in the device, so you can make, right now we're looking at rail 1, as you could see by looking at the cursor on the top right-hand side. You can make rail 1 turn on dependent upon rail 2 being within regulation, and then staying on dependencies. So in this case, if you clicked rail 2 and rail 2 went down, then that would pull rail 1 down with it. And then it has shutdown modes that are shown on the right-hand side. Over here, you're showing the rails that you're showing the details for. So I'm showing rail 1 right now. If I click right here, it'll then pull up the information relative to rail 2. You also have the ability to rename rails if you chose to. So I just renamed that rail B. So that'll then show up in the graphical design as well. Makes it easier for you to track your design. There are many other configuration options for more advanced configurations, things like phase and rail configuration. If you wanted to make this a multi-phase device, you can do so. You can configure GPIO in the device, etc. But that shows the basic configuration. Now I'll move on to the design screen. So the design screen, we're really trying to strive to make the product very easy to use. So let me show, for instance, I'll switch over to a different rail, which in this case is rail 2. And you can see here, you can select the power stage. So are you using a module? And here we list some of the modules that you can use with the digital controller. Or you can select discrete components. So if you want to select discrete drivers, you could do so there as well. Basic information about the design is included here. And then you can click here and you put information about your schematic. So note, we will automatically configure and select many of the components in the system just by clicking those boxes. And here's where you add components. If you want to add capacitors, all you do is you click on the boxes and it will then go ahead and add the component you select. Plus, you have the ability to put your own components in. If you wanted to add new components to the library, you can do that as well. So that's all part of the tool. If you go down further, it has information related to design to device synchronization. So if you wanted to do things like configure and calibrate your current limits, and you have the ability to do that as well as everything else that's listed there. For multi-phase, you have the ability to phase shed. So when you're looking for more efficiency for a multi-phase system, here you phase shed based on current levels that you select. You shed down to a certain number of phases, so then it'll turn off the other stage until the current's over a certain level. And here is, again, the hysteresis for the current measurement that'll turn on and off phases. One interesting feature of the digital controller, we can automatically tune the compensation. So by selecting auto tune here, you can then put information about your target phase margin, V in and V out, V in max and V in nominal percentage, so for deviation, and then select auto tune and it'll pick the compensation for you. Going back down the list, this has information about compensation. In auto tune mode, this will not show up because you're asking the computer to actually select your compensation. But in manual tune mode, you have the ability to select your pole and zero placement. As you can see here, we're showing a couple different graphs. One is the Bode plot for the power stage, and the other, this is time simulation. So this is with the compensation that's in here on this specific rail, this will show how far during a transient, and in this case a transient goes from 25% to 75% of the rated current, which is 10 amps, at 1 amps per microsecond. This will show the deviation expected on the output. And it's a simulation, but it's proven to be relatively accurate. So moving right along, I will show some information on monitoring. So in this case, we're monitoring the output, and at this point in time, the output is actually turned off. So I will go ahead and turn the device on to always converting. And there you can see the device is going up to about 1.8 volts. And showing the input current is obviously very light in this example. And it's monitoring temperature and output current, input voltage, things like that. So this is really just more of an indicator of what is happening with your power supply when you're in regulation. Note you do have the ability to configure your overvoltage and undervoltage information as well as overcurrent and undercurrent information while in these specific screens. So status will tell you information about the power stage itself. Are there any faults that weren't cleared previously? This will store this information into the device. Here is logged faults. And then it'll also show information on peak recordings for you, so you can read that information back at a future point in time via PM bus. And then security. So we have the ability to have certain commands that cannot be overwritten once you're out in manufacturing, and your application is out in the field, if you wanted to protect what information could potentially be overwritten there. So that's what that specific command does. So as you could tell, there's a lot of flexibility built into these digital power controllers to really help simplify design and really adapt themselves for changes in design. So that's one of the big values of digital power, and it's one of the reasons, in specifically things like monitoring current, that has made this a very nice match for the Xilinx Spartan 6 and Vertex 6 FPGAs. So again, I'm Steve Bakota. Thank you very much for spending the time going through the tool, and please contact one of our field applications people so we could do a more in-depth demonstration and drop off a demo board so you can play with it as well. Thank you for your time.